So this will be your joint work with Vicent Payardo.
Yeah, who is in
I
the
have
audience.
never, yeah, who's in the audience, but I have never met Vicent Payardo.
No, last year he was a baccalaureate student. So the whole work starts from baccalaureate thesis degree.
Okay. So hello to Vicent Payardo, the co-author. But now, Salva, you're at home or
Yes.
at the department?
I just came back from school, from leaving the children at school. So there was no time from 9 to 9:30.
Schools operated regularly?
Pardon?
Schools operates regularly?
Yeah. Yes.
Yeah? The same in Poland still, but...
Yeah, school is as usual. If one person in a class has coronavirus, then the whole class is confined, but not the whole school.
Okay.
Adesso quindi fra un po' mi connetto. Cioè comunque io adesso ho pensato a queste domande e poi la chiudo, io non la voglio fare.
We have some noise in the background. I don't know who is that.
Hi, Rico.
Hi, Koto.
Hey, Rico. Nice to see you, Rico.
Hi, nice to see you.
I caught your recording, but I couldn't make the talk. I'm sorry. I'm going to put myself on mute.
Yeah, Glenn, it's nice to see you. No, I recognize you. How is it going?
yeah, I was telling, it's nice to see you as well. I'm good.
A long time no see, right?
It's been many years.
Oh, yes.
Okay, let's wait this one more minute so that nobody loses anything. Oh, there is. Is this now Professor? What's the name? Professor Yamamoto, or I don't know.
Hi, Piotr.
Hi, how are you?
Good morning, everybody.
Good morning.
Morning. Good evening.
Morning or evening.
Or evening.
Good morning.
Okay, I have 9:30 here, so I guess let's start with the morning session. If you're ready, Salva.
I am ready.
Yes, so we will now have Salvador Moll, who will speak about an augmented Lagrangian model for signal segmentation. Please, go ahead.
Thank you, Michał. If you hear me well, then I would like to thank the organizers, because for me this meeting is very important. I mean, it's difficult days now, and it's nice to see all of you, and that science still goes on, and you're doing very hard science, nice science, I would say. And it's nice to communicate with you and to see you and to give us some let's go, let's continue doing this. So thank you very much for the organizers. For me, I really appreciate you providing this. So today I would like to speak about a very simple model. I mean, this is 1D model, this is signal segmentation. And this is a joint work with Payardo, who last year was a baccalaureate student. And we started to do some segmentation study. And we end up with this model that I think that it provides some new insights on the classical Manford-Shah model, but in 1D. So let me present you first of all.
You who are not familiar with this part of image processing, so segmentation, you have some information, this is information, and you want to extract some particular information that you find interesting. So for instance, here you want to extract the man and the bag and the handbag. And so this is you call the foreground, and this is you call the background. So you want to divide the image into two phases. The one phase is called foreground and the other one is background. So this is the end of the whole story when you segment the man and the handbag. So this is for image. For signal, this image, suppose that you have a noisy signal here, and you want to extract some piece of information, which in this case is not two-phase because it's not foreground, background, but it's multi-phase because you want to extract several level sets. Okay, so this is done with the well-known condat algorithm. And if you put an input a noisy signal, then it gives a piecewise constant solution. So this is what segmentation is about, and let me present the most classical model for image segmentation, which is the Manford model. It goes back to the 89. So suppose you have a given image, which is from a domain into 0, 1, so it's a grayscale image, and you want to obtain a compact set, which represents the contour of the image, and a regular function outside of the compact set, minimizing this energy here. So here you want that your solution is close in the L2 norm to the given data. Here you want that the perimeter of this contour is not too big, and you penalize with lambda and beta, 2 parameters. And here the solution has to be smooth outside of the compact set. So this is the most classical model for image segmentation, and it has been very used. So in the case for two-phase,
in the case you have a foreground and background, then I cannot see. Okay. Then the solution should be constant inside of the set provided by the compact set, so inside of the curve provided by this compact, inside of this curve, say, and outside. So constant inside the domain and on different constant outside of the domain. So in this case, the Manford functional turns out to be this one. So you look for a set and two constants, and you want to minimize the perimeter of the set and the difference between the function and the constants in the L2 norm. Okay. So, okay, this is two-phase segmentation. So let me explain the difference between Manford and this two-phase. So this is original image. Here you do segmentation with Manford. So you look for that the function solution is smooth inside of the contour, and this is two-phase. So it's black and white. So you only care for the contours here. Okay, so let me explain now what is the here parameter lambda here. So suppose that you have this is your given image, which is the Sierpinski carpet, and if lambda is small, then you penalize a lot the perimeter of the solution. If lambda increases, then you penalize less the perimeter. So the solution, the minimizer prefers to jump. So when you increase lambda, then you get more resolution. This is the role of lambda. Okay, so now let's move to a very smart technique introduced by Chan and Besse in 2001. So they applied the level set method for obtaining minimizers or critical points, let's say, of the two-phase Manford problem, because the Manford problem is not complex. So suppose that the domain is given by the zero-level set of a smooth function. Then the two-phase Manford functional turns out to be exactly this one, where H is a Heaviside function. So critical points of this functional, critical points, but given C1 and C2, so you want to find phi. Critical points are stationary solutions to the gradient flow of this functional. Since the Heaviside function is not regular, then you cannot compute the gradient flow, but they approximated the Heaviside function by a smooth approximation, and they obtained this gradient flow. So the critical points of the approximated functional were stationary solutions to this gradient flow. Okay, but Chan, Sedoglu, and Nikolova 5 years later found that critical points to this functional, since this is near zero, are exactly the same critical points of this functional. So now you want to minimize, this is phi, sorry, you want to minimize phi in 0, 1, this energy functional. Given the constants, you want to minimize phi between 0 and 1, this functional, which is the total variation of phi, and here the difference between the L2 one. So if phi is binary, so it's the characteristic function of a set, then you recover here the perimeter of the set, and here this is 1 and this is 0, so you recover exactly the Mumford-Shah two-phase functional. Okay, so the Chan-Desses algorithm is first you choose phi 0, so you initialize. You compute the constants. This is just done by integration. Then you run the gradient descent method, and you obtain the next approximating set. Then you recompute the constants, you come back here, and you repeat this until the algorithm converges. This has been widely used. There are, I would say, hundreds of sophistications of this algorithm, but I will stick to this very basic one. So the main drawback is that the functional is not convex. So the convergence of the gradient descent method is not ensured. And it depends strongly on initialization. So you have to know something for the image in order to make this converge. Instead, the second functional, this Chan-Sedoglu-Nikolova, is convex functional. But here the minimizers might not be binary, might not be the characteristic function of a set. And it is not known if when you run this algorithm, in the end, you will get a binary solution. So maybe minimizers that do not coincide with Mumford-Shah two-phase minimizers. So let me explain some of the malfunctioning of the gradient descent of Chan-Besse. Suppose that this is the signal, and you want to segment the signal. So if the step of time is very small, then you get stuck at a local minimizer. You don't get the real minimizer with fixed constants. If the increase of time is very large, then you get the same. You get stuck at a local minimizer. If the increment of time is okay, then you can get the real minimizer, but the problem is that the algorithm does not converge in this case, because it goes from another global minimizer in the next step, and then repeating like that. So these are the main problems of the gradient descent for Chan-Besse. Okay, so our proposal is we take the Chan-Sedoglu-Nikolova functional. This is with fixed constants. And then we say, okay, but we don't know these constants. We want to do the algorithm in a one step, not into step and recursive. So we Lagrangian, and it's based on a work by Brown, Bresson, and Chan, who did it numerically. So we, instead of minimizing one function, we minimize three functions now. We minimize this functional, which depends on three functions. So we have the same functional here. We add the indicator function of u. So this means that this is 0 inside of 0, 1 and plus infinity outside. So we ensure that u is between 0 and 1. And we penalize strongly, on the gradients. So when epsilon goes to 0, then we expect to end up with constant solutions. Find exactly which is. So very easily we see that given a function, this is not true. This is a function in 0, 1 because it has to be an image. So there exists a minimizer. There exists a minimizer in B2. Okay, and this is very easy to prove. The proof is we take here, take the functional, and we consider this auxiliary functional. We just impose B1 and B2 to be between 0 and 1. So this function is lower semi-continuous and it's coercive. So there exists a minimizer. And then we prove that a minimizer of f epsilon then also satisfies that B1 and B2 are between 0 and 1. So minimizer of f epsilon is a minimizer of G epsilon, so there exists a minimizer. This is very easy.
Moreover, by convex analysis, we can obtain the system of PDEs for that minimizer satisfy. Okay, here this is the subdifferential of the sum of the total variation and of the integral of the indicator function. Here the subdifferential of total variation, and for B2 exactly the same, the subdifferential of the total variation. Okay, so in order to get a full description of this, we want to obtain who is this guy here, the subdifferential of the sum. And then it turns out that the subdifferential of the sum is just the sum of the subdifferentials. And for this, we just rely on a technique developed by Ken Shirakawa. And we just apply for this case, and yeah, it works. This subdifferential of the sum is the differential of the sum, or the sum of the differential, sorry. So this is for any dimension, and now I will stick to 1D for the 1D case. So omega will be 0, 1. I will remember the characterization of the subdifferential of the total variation in order to get something which we can work with this. So in 1D, this is only 1D, an element is in the subdifferential of U if there exists Z in the Hilbert space 0, 1, such that this is less or equal than 1 almost everywhere. B is minus the derivative of this, and these two measures coincide. So this is the total variation measure. If Z is in this space, then in 1D, this is included in two continuous. So this is continuous function. This is a measure. So this has perfect sense here. Okay, so with this, we can state that P is satisfied by the minimizer. So the ZUX is this exactly this plus G. G is in the subdifferential of the indicator function 0, 1 of U. Here we have to put U. Here set B1 is in the subdifferential. It corresponds to the subdifferential of the total variation of B1, and this vector corresponds to the subdifferential of the total variation of B2. This is the system of PDEs that allow us to obtain more things. So the first thing that we obtain is that, okay, if epsilon is small enough, but epsilon does not depend on other things, only on lambda, then B1 and B2 are really constants. And they do not depend on epsilon. So the solution does not depend on epsilon for epsilon small. So we don't have to care about convergence when epsilon goes to 0, because this is guaranteed because we have minimized it. And this is crucial for us. We just sketch the proof because it's very simple, but it only works in 1D. So the proof comes from this fact that if we have a vector field corresponding to the subdifferential of total variation, then this vector field, deep C almost everywhere, coincides with the Radon-Nikodym derivative of the total of the variation divided by the total variation. So in particular, C modulus is equal to 1 d of C almost everywhere. And from this,
second equation, for instance, which is this, you integrate from 0, which is the boundary. Remember that set is in H01, so at 0 is 0. You integrate from 0 to a point where this set is 1 or minus 1, and you get a restriction on epsilon. So when epsilon is less than 1 over 4 lambda, then B1 is constant. And it happens the same for B2. Okay, and this is the right expression for the constant C1 and for the constant C2. So it's a kind of average.
to continue, we have to make an assumption on the data. And the assumption is that the data is not too oscillatory. So for any level set, the boundary of the level set, which are not in the jump, has L1 measure 0. And this is to prevent that some level set is a fat Cantor set. Okay, so with this hypothesis, with this assumption, you are excluding this, that a level set of the data is a fat Cantor level set. It's a fat Cantor set. So the result is given any two constants fixed, and you only want to minimize the functional, but only with respect to the first variable. This is fixed. So if you give me a minimizer, then there is another minimizer, which is piecewise constant or binary. So it is piecewise constant when it is not 1 or 0, and it has the same energy. Okay, with this hypothesis. So we have reduced minimizers to being piecewise constant when this is not 1 or 0. And so with this, the next step is, okay, now we plug in the information of that we have for C1 and C2. And with this, we obtain that all minimizers are either constant or binary. So it cannot be piecewise constant. Either they are a constant or they are binary functions. And this allows us to show that the set of minimizers of our functional coincides with the set of minimizers of the two-phase Mann-Forscher model. We just take the set to be the characteristic function of the level set equal to 1. So our minimizers coincide with the set of minimizers of two-phase Mann-Forscher. So that is almost the end of the story. We have proposed a model which provides the same set of minimizers, but in the proof we obtained two important properties. But as far as I know, they were not known. Please, there are some experts in the audience, so correct me if this is not true. But the first one is that if the data is piecewise constant, then the jump set of the minimizer is contained in the jump set of the solution of the data. This is only for the case that the data is piecewise constant, just as for the root inertial fraternity. So this is not true for bigger dimension. For instance, suppose that the data f is the characteristic function of the square. So here we can reduce drastically the perimeter without changing too much the L2 norm of the difference. So this has strictly less energy than this. So this cannot be a minimizer. Okay, so the jump set cannot be contained here. In fact, the jump set, when you compute the jump set, is exactly this, but this has been rounded here. Okay, this is the numerical solution for this as initial data, the characteristic function of this as initial data. And this has to do a lot with calibrability, but I'm not going to enter now into these things. This is not true for bigger dimension. In one dimension, all intervals are calibrable, but in 2D, this is not the case anymore. The other important property is that the jump set of any minimizer is contained in the boundary of a unique level set. In a multi-valued sense, because if the minimizer has jumps, then the jump, I mean here, it should be this level set, so in the middle. So this, I would say, I am saying in a multi-valued set. And this is very important. This is very important because this knowledge permits us to obtain a trivial algorithm for computing minimizer. So the jump set is contained in the topological boundary of a source level set, and it is a binary function. So you can design this algorithm, which is very trivial. You just divide the range into n parts, equal n parts, and you just play this game. You descend this, and here, this is the intersection. This is a level set of the data. So here it divides this into 1, 2, and 3 pieces. So you compute all of the energies of all of the combination. This is 1, 0, 1, 1, 1, 1, 0, 1, 0, and so on. And you just keep the lowest energy. And you do this with all the levels, and then you end up with a minimizer, because the minimizer is contained in the jump set. This binary function, the jump set is contained in a unique level set. Okay, so this has always a solution, numerical solution. I mean, there are no problems of convergence and so on, such as in the gradient descent scheme, and this is very fast. This is real fast. So I will finish with an application.
Speech segmentation. Suppose that this is this phrase. In fact, this is a phrase in Spanish. This is hola, ¿qué tal? Normalized. Then you smooth. This is the smooth signal. And then you run out this very trivial algorithm and you obtain this segmentation. This segmentation is exactly. And all of this process is done in less than 1 second. It's really fast, this algorithm. So yeah, it always converts to a minimizer.
To conclude, I will present the conclusions here. We have introduced an augmented Lagrangian model, and we have obtained existence of minimizers. If the data is not too oscillatory, in the sense that all level sets are not fat Cantor sets, and with epsilon only depend on lambda small, then minimizers are binary or constant, and they coincide with man function minimizers. You have obtained some other properties of the jump set. And we have developed a very fast trivial algorithm. And the problem, and we are going to start working with this, how can we extend the results to the case? Is it possible? Is it possible? So thank you very much for your attention. This is all I wanted to say. Thank you.
Okay, thank you, Salva. Oh, very, very nice Polish here.
Thank you.
So, of course, now any comments or questions are very welcome.
I wonder if Masson could offer us a comment on this work.
I don't know, probably he's smoking at the moment, so maybe.
Outside.
So let me ask you a question.
One small question. Why the vector field belong to H0, H10?
Because it's Neumann boundary condition.
But
so
zero is
boundary
zero. But it's H1. No, Neumann is H1, no H10.
No, set has to be 0 at the boundary, Mathon.
Yes, the vector field is in 1 dimension. Yeah.
Yeah.
Okay, thank you.
So this is before. Yeah, you can put set equal to 0, set in H1.
Yeah.
It's only 1 dimension. I mean, existence of minimizers and that existence of minimizers that is the subdifferential of the sum is the sum of the subdifferential does not depend on dimension, but the rest all of them depend on 1D.
Okay. Thank you.
I have a question.
Please go ahead.
Have you thought about the opportunity to introduce some constraints in this image segmentation? Just one example. Assume that you have a two-phase image or binary image, and you know the number of the pixels, voxels belonging to the, say, rigid body. So that this is a kind of constraint. Do you think that such constraint image segmentation could be treated by some generalization of the method you presented?
I mean, for image, we have to change the mind, because nothing works if we just keep on the Euclidean norm of the total variation. So, because the total variation Euclidean norm just provides round things. It rounds sharp corners. So our method cannot be applied to 2D if we just keep with the isotropic total variation. So if we change it to an anisotropic total variation, for instance, L1 total variation, then this is what we are trying to obtain now. then squares or polygons should be stable.
No, but I'm wondering if the question wasn't even doesn't make sense even in 1D. Is the question just about some kind of volume constraint? So, you know, like how many pixels are supposed to be 1 and how many pixels are supposed to be 0, more or less?
It's exactly related to the volume conservation.
Yeah.
Preserving the volume in the image segmentation. Okay, thank you.
I don't know, I have to think about it.
Good.
I have to think about it.
Okay.
I really don't know.
Interesting to me also, I mean, in other models too, because I haven't seen people doing this kind of constraints. I don't remember at least. But it seems kind of easy at first glance. In any case, I wanted to ask about something different, Salva. You said that there is this, you have this assumption that you don't have these fat Cantor sets and so on. So I was wondering what happens in that case. In that case, can you have these minimizers which have both somehow piecewise constant part and this binary part, or what happens then? What's wrong?
This is just a technical assumption for us.
Okay. So,
I mean, my impression is that that does not change too much the result, but this is just a technical assumption. We cannot get rid of this because of our technique, but.
Okay.
Yeah, because I mean, the problem is that the result here, either U is piecewise constant when it's not 1 or 0. So this is not even clear to me if this is not really a piecewise constant function in the whole. And it's because of this kind of facts. Because we want to exclude these pathologies. But these pathologies we are only excluding outside of 0 or 1. So this is the same type of pathology here that it can be in 0 or in 1. I really don't know. But my impression is that it's just a technical assumption.
Okay. Thank you. In any case.
Let me ask you another question. When I compare your pictures with pictures presented by Yoshi yesterday, I have an impression that there's a deep link between your work and Yoshi's work. Did you think about the connection?
No.
Not yet.
Not yet. Not yet. Sorry, because yesterday I couldn't follow too much the meeting because I had 5 hours of lessons. So I had no time to think about connection between my work and Yoshikazu.
But this comment prompts me to make an announcement. Yesterday I sent out links to the recordings. If someone did not get any message about recordings, please send me an email. And I would like to ask you another question, Salva.
Yes.
You were segmenting the sound sinus. I can somehow understand this two-phase segmentation of images. This is purely black or white, but I don't understand what is the outcome of the sound segmentation when you have just two, I mean, maybe not two, a few levels of sinus. Could you explain what is this sound segmentation? How does it work?
This say it again, sound segmentation?
Yes, but at the end you presented an example.
Yes.
Of your work applied to the sound segmentation.
Yes. Speech. Yeah.
Speech segmentation.
Yeah.
And could you explain what does it mean in practice? Because
I mean, here you have a phrase. This is a phrase. So you want to get rid of empty pieces of the speech and the noise. Well, the noise is different, but the first thing is that you want to get rid of empty things. So you want to keep the words, say. So for keeping the words, you just do segmentation and you say this is a word, this is a word, and this is a word, and you can forget the rest.
Oh, I see.
And then if this is a word, then you can process it. You can do the noise here, the noise here, and the noise here, and you just don't have to care about these things here. You can do lots of things. It's just for keeping the words.
I see, understand now.
This to face. So this can be a two-step thing, because first you just extract the information, and then you work with this information, only with this information.
I see. Thank you.
But here we needed to smooth out first, because here if we do, you just take real speech signal, this has thousands of discontinuities. So this algorithm is not fast, because you have thousands of discontinuities. You have to take as many intersections with the with the jump sets here, and to count all of them. So you first smooth out, and then it's very fast.
You seem like talking about real life applications. So is it indeed the case? Is someone using this this algorithm?
Well, now there is nobody using this algorithm, because this is, I think that this is new, and we have still not submitted. We will submit the next week or in 2 weeks. But Vicente Payerdo, who is there, can you tell more? Can tell more something else about real applications of this? Okay. I don't know if he's willing to talk or not. Vicente, can you say something about this?
Yes, please.
Hello.
Hello.
So I guess we have Vicente. I mean, he unmuted himself, I believe, or someone unmuted him, but I don't hear anything.
Hello.
Ah, yes. Hello.
Hi. How are you?
How are you?
So we want to know about the application of that algorithm. First, we have to know that we take signals as a discrete object. So in that case, when you use the top part of the images, we have a discretization of the range. So we can fix one number, for example, a partition by 1 per 100, per 10, per 20, whatever you want. So in the case of application, we could use to segmentate speeds, segmentate any just dimensional object that you can take as a one-dimensional object. For example, code, ticket code, or that kind of things.
A code?
So,
sorry?
A code.
A barcode.
A barcode.
A barcode. Okay. I see.
So the importance of that algorithm is because is that you take the algorithm to explore other way that not a convergence one, because it's important to find that algorithm with a discretization, it only depends of the hardware power that you use. It not depends of the problems as divergence or the kind of things that with gradient descent we have.
Yeah, but I think that the question was if you think that this can be applied in real life, this algorithm.
Yes.
Yes, I think it's really applicable in the case of FP segmentation, because right now we use a lot of deep learning algorithms that use a comparative sketch. In some cases, we have a lot of misunderstand of the training data in the deep learning field. And using that kind of things, we can to reduce the complexity of that kind of studies. So it's really important to take care in that kind of trivial but powerful algorithms.
Can I encourage that you apply for a patent? I think if you can use it to assist all the AI deep learning, then it could be incredibly popular.
If we manage to do it in 2D, then I think so.
Yeah, okay.
But you say that somehow it's important here that these jumps are preserved, right? Or something like this. I mean, for some reasons.
I mean, the proof of these two results here, it's practically the same. So the important is the second one. That when you do segmentation, then you stay at about this, all which is 1 is about this level set, all which is 0 is below. And this is very important for designing the algorithm. But the proof in this case is the same for property, for this property and for this. It's just the same proof.
I see. So I guess it's an example, going back to these applications, I guess it's another example of like, okay, you have this neural network algorithms, which are very powerful, of course, but you have to do a lot of this learning and so on. So it's you need a lot of resources for that. But here we have something like this simple algorithm that you can do really fast, and then it can also assist learning. So I guess it's typical answer in this kind of case when someone asks, okay, but is this kind of variational image or signal or data processing actually useful? So I guess here we have another example of that. So I don't know, do we have more questions or comments or? Okay.
Instead of just a.
I can ask.
Oh, okay.
Oh, we have so Glenn was first, so please go ahead, Glenn.
Okay, just a simple question. So one of the challenges with feature detection in real life applications of image processing is overlapping objects. So when you had the example at the beginning of the man with the luggage, then you can imagine if, say, the man is green and the luggage is red, then if they are overlapping, then your neural network will be able to be trained to say, okay, these are two separate objects. So there's two objects. And it's kind of a big challenge to have that working in a robust way. I just wonder, when I was listening to your talk, you have a two-phase model, which basically is on or off if there's a feature or something. I'm very curious if it could possibly be changed to be a multi-phase model, and you could say, oh, here's sort of a depth of a feature, and then you could have sort of ridges that would sort of indicate that there's two objects overlapping. Do you think that would ever be possible?
I'm not sure about that answer to that question. I mean, not as we have worked, but I cannot tell you that this is not the case. I mean, could be.
I suppose
Salvador, that multi-phase also work. Yeah, say.
Suppose the question is, can you do vectorial case, basically?
Yeah, not vectorial case. I think that the question was multi-phase.
Yeah, but you can encode multi-phase in vectorial.
Yes. I have not thought about it, but I think it could be doable. Yes.
Cool.
I don't know. I mean, let's try and see what happens. Yeah.
I think it'd be very cool.
So you are saying that this is somehow difficult for these neural networks. That was the motivation for your questions.
It's a problem. a lot of my colleagues at the university here are working in AI, and they do implementation of algorithms for example, when the Google car is driving around and trying to detect, you know, if there are things in front of each other, and you know, how many, like when does a car stop and a pedestrian begin, that sort of thing. And there are, yeah, they're doing a lot of research, but they don't exactly, they're not doing anything more sophisticated than huge data sets and training neural networks to recognize statistical examples, so that when a genuinely new situation comes up, they can fail, and that could be very disastrous when you have something like a car that's driving itself. So obviously they're really concerned about this, but they're not doing any variational analysis as far as I know. It's just neural network training. Anyway, just a question.
Thank you. So, okay, Ken Shirakawa also wanted to ask something.
Thank you. I have a short question. Can we expect to estimate the convergent order of such kind of algorithm?
I mean, yeah, sure. It only.
On the,
for example,
on the size of the mesh you do here, because you compute all the possible combinations. So it only depends on the size of the discretization here in the range. So this is the distance.
On this. Yeah. It depends on this. It's all of this.
Okay, I didn't actually get that you impose a mesh here. Okay, that makes sense, sure.
I mean, yeah, we have to compute numerically all the possible combinations here, but we have to do a mesh here in the range. Okay, so the minimizer is, yeah, if it's 1 or 0, then it's close as the discretization of the mesh here.
Then how much time can you get such result?
I mean, for this is less than 1 second. The whole process. Less than 1 second.
How is the speed compared with other algorithms?
Well, it depends. When you have a good initialization of Chambese, then it's the same speed as Chambese. When you have bad initialization that goes to a critical point, which is not a minimizer, a global minimizer, then you are stuck there, and the algorithm of Chambese does not convert to a real minimizer.
Oh, I see. Thank you very much. Thank you very much.
You're welcome.
Okay, I don't know if this break was longer than usual. In any case, any other questions or comments? Okay. Well, if not, then I guess we can thank Salva for his talk again. So
thank you very much.
Thank you very much, and we can start preparing the next speaker, who is Piotr Mucha, I suppose.
I think so.
Okay. So do you have any slides or anything, or are you just going to?
I have something. I would like to start with some, how to say,
please do not start. Okay, so you have like a prologue to your talk right now.
Somehow, yes.
Okay.
Maybe not to talk, but to the meeting. So usually, I mean, the first approximation meeting should be in May this year, yeah. And then because of coronavirus, we shifted, hoping that this is over and so on, but finally we meet online. And in this meeting, there is a hidden one event related to my old dear friend. And I asked him 2 days ago if he will be present at the university just to do this personally, but somehow he said that no, I'm going to Solt, near mountains where he is living usually. So this is far away from me. So I may say, Piotr, that I found something. I found something here from Jamaica. I know that you are a fan of this fluid from Jamaica. So as we meet at faculty, I hope soon, so then we can empty this bottle, okay?
Thank you. This sounds cool.
Pardon?
This sounds cool.
Ah, yes, yes, okay, but you know, I'm also old as you, so almost old as you, so my hearing is not perfect, so I understand this is old school, but more or less this is the same. I may say that to the field I was introduced by Piotr several years ago. We did some nice works in this field. This field is very nice, but unfortunately, due to problems with administration, we stopped our collaboration because we start to be overloaded. And this is the reason my current talk is a bit away from the mainstream of this meeting, and it's related to, say, free boundary problems. So this is horribly unlocal, but give me now how to do this. What I shall do to share the screen?
In the bottom, you should have a big button in the middle.
Share the screen.
Green
yes,
button.
Yeah.
Share. You see this?
Oh.
Okay, very well.
And now how to do this? No. I'm not familiar with this. Okay, now it's good.
Yeah.
Okay, so.
But we still have 2 minutes, so let's wait. Maybe somebody will.
Okay, so then I will continue the story with Piotr, because then there is, say, informal talk. So we had some times ago, it was, say, 10 or 20 years ago, in our age is normal. We had some brilliant idea how to solve this all nonlinear, highly nonlinear system with highly anisotropy. We even introduced the notion of almost classical solutions, claiming that all these flat things are indeed very, very smooth. Byproduct of this collaboration is Michał Łasica somehow. He did PhD in this field together with me and Salva. So there is some, how to say, pozostałości. Jak to jest, Michale, pozostałości?
Remnants.
Remains or remnants. I don't know if that's the
something like this. So this is good point. Maybe in good time I will find time to return to this subject, because as Salva told, this is related to somehow way of minimizing some functionals, which is related to this very fancy things like machine learning, and all things are around this. So even in partial differential equation, we have it at the beginning. So now I can start to talk or not yet?
Yeah, I think you can. So now officially we have Piotr Bogusław Mucha from University of Warsaw, and he will speak about D'Aprato and Griswart on free interface, apparently. Please
okay, thank you, Michał. I would like to say that this is my great pleasure to be with you. Honestly, I'm not a fan of such a meetings by internet, because personal contact is still better. And then it's easier to communicate. And first of all, as you see only my head, so this is very difficult to use all this body language and other undefined aspects of communication. So what I plan to do today, I will talk about very, very classical stuff related to free boundary problems. In generally, problem is that you can imagine classical results of Всеволод Aleksiejewicz Sołonnikov, who comes from Ładyżańskaja school. So mostly we have 100, 200 pages of computations. And at the end, we have the result, as we understand all these 100 pages, that as we have, say, a ball of water with free boundary, so then small motion of it preserve this shape in time, globally in time. So the basic problems are related to find a good linearization with full information about the property of the solution. So somehow we need to show that this shape we consider at the beginning, and rather its linearization around this shape, is stable in some sense. So then we have a chance to show global stability. So as we look from D'Abrato and Griswold, this is quite old picture, as you know, as you can see. So I'd like to talk about an approach which somehow make a synthesis of this computational method to abstract theory of semigroups. Okay, I have question concerning, can I have this magic pointer or not?
You can have a magic pointer. You will find it at the top of the screen. It should be there. In the
options.
There should be an option annotate.
Yes.
Somewhere.
Options. Okay, so I need to use. No, I have options annotate. Okay.
Yes, and there are many. Yeah.
Okay. So now it's working. But this
you
is
also
not...
have. You should have spotlight or something like this, and spotlight is this nice laser pointer if you want it.
No, this is not this. Erase. Okay, so maybe I will get it. It's difficult to me, as you see.
But this eraser anyway, is also a nice pointer.
Eraser is pointer. Okay, you are right. Okay, so then the paper is, my talk is based on some paper which is almost done as usual from 2 years. There is a finite number of authors. The collaboration was started in, I will tell a story about this because also this is related with some mathematical way of thinking about the results. So all these people are somehow connected with some parts of the theory. And from that reason, we start to collaborate. Of course, the guy who is writing in all the thing is the youngest one, Patrick. And now he tried to edit the text. So the idea of the talk is not to present the estimates, to present this myth, so-called, but rather to say what is the main goal of these approaches, what are obstacles, and what we need to do this. So first of all, we look for classical approach. So as we return to the picture, so then classical, it means that we have water and air, and these two phases are very well separated. As we look for this, say, white form here, so this part of this interface is not fit well to what I plan to talk. This is somehow important that we will have to distinguish two parts with the interface which somehow is smooth. So in order to do this, the model we consider must have property of good linearization. So it means that instead of nonlinear system, we need to have a chance to consider as a linearization with small perturbation. Of course, this is free boundary problem, so this is horribly unlocal. And at the level of the nonlinearity, this is true nonlinearity, but of course this is more complex to explain. Second, as we have this linearization, so this linear system must be well posed in some sense. So indeed, we need to think that the system we obtain possess so-called maximal regularity property. So it is like parabolic elliptic system. So this is not only the case, because also for some damped hyperbolic system, we are able to get it. For hyperbolic parabolic system, like for a compressible Navier-Stokes system, we can do this, but in generally, this is very, very restrictive. So as we consider free boundary problems, so then we expect that the model equations must somehow smooth out the system. Of course, there is some different approaches. For example, for Euler system, where this approach does not work, but then this is very, very tricky and based on geometrical properties of the equation. And the last thing, which is horribly important just to consider free boundary problems, is control of the free boundary in time. So in few words, we shall remember about one thing, that as we make linearization and obtain the solution, so then all constant depends on the boundary. So it means that as we look for this, as I told, this classical work of Solonnikov, it means that we need to control all properties of free bound, maybe not free boundary problem, linearization of free boundary problems in the construction of constants. So very often abstract approach does not work because we are not able to control the constant. Okay, so what does it mean, good linearization? Good linearization is, first of all, that system somehow at the level of the equations, I'm not talking about the non-local connection to the boundary, because this is very highly nonlinear, but at the level of the very system, so this must be somehow quasi-linear. So very good example, which I will talk about, is Navier-Stokes equations plus free boundary problems. So it means that at the level of the equation, nonlinearity cannot be too high. So as we think about other models to viscous fluid, and we take non-Newtonian fluids, power law type systems, so instead of that viscosity is a function of symmetric gradient of velocity, so then we have no chance to have good linearization. So then all these systems, all this approach collapse. And then we have free boundary problem, and of course we have many type of free boundary problems. Mostly we have so-called free conditions. So this is more or less Neumann boundary condition. So in one phase system, this is like this. We have the fluid, and then, or you can see the fluid, and outside the fluid we have, for example, constant pressure, and this is the boundary condition. Very often, at the beginning of the story related to free boundary problems, there was considered also stress tension at the boundary, which smooths out the interface. This is somehow cheating of the problem, because from mathematical viewpoint, it means that at the free surface, we consider Laplace-Beltrami equation, which momentarily smooth out as this interface. This is something which is very technical, but for all people who are working with this stuff, it is clear that of course we must to pay very often tens of pages of computations, but these computations are rather just tediously technical. This is not a question of advanced mathematics, some ideas, but this is rather related to technicalities. So as you see this problem, very often they say that this is more natural, maybe from viewpoint as we consider a ball of water, a drop of water. So then the stress tension really appeared, but as we add some soap in it, so then the stress disappeared. So from mathematical point of view, this is huge simplification. Okay, maximal regularity. What is the maximal regularity? So again, we have two schools of it. So one comes from Fontanki, from Olga Aleksandrovna Ładyżeńskaja. So then we have classical estimates for in given space, we consider given equation and obtain the optimal regularity estimates for the linear system. And second is abstract problem based on so-called semi-group approach. So this is I mean, one of the creators are these Dabrata and Griswold. Very nice. My favorite result in this field is to Giga and Zor around 31 years ago, as far as I remember. It is about this type of estimate. So more or less how we may look for this abstract maximal regularity, we have elliptic operator. We can think about this like a minus Laplacian. It can be any well-posed elliptic operator with some properties of analyticity, sectorial, and so on. It depends on the theory. And then we have some parabolic type system. We can name it. Of course, this must not be only the parabolic because A can be just one. And for simplicity, we consider just zero initial data. This is just, how to say, technicalities. I'd like to avoid the trace. And then we say that this system admits maximal regularity estimate as we are able to prove the following estimate. So UT and AU are in the same space like Z. So good example is as we forget about the time, there is no time here, and we think about elliptic system in the space, and we know that as F is just continuous, so then there is no such estimate. So this is good example that not in all spaces this type of estimate is valid, even as we consider very classical operator. So of course, mostly in LP spaces and other things, there is no problem to define it. So we have this. This is nice object. And second is controlling time. Controlling time, this is important because as we look for drawing, let's try it. No. As we look from our free surface, so somehow this is a question of, say, T0, and after that we have T1, yeah? So then we see that as we consider this stuff of object is of course changing the shape, but we are afraid of this type of catastrophe. So looking locally, as we using local coordinates, everything is smooth, but the realization creates a cross sections, which somehow is related as we have the wave. So then here appears some singularity, and singularity is not the case that solutions blows up. We have just geometrical catastrophe. So this is somehow important. Let's remove this nodes. And as we return to this linear system or non-linear system, so what we need to have, so expectation are that we need to have a decay. Usually in classical result of Solonnikov, it's dedicated to compact boundary case. So this is bounded domain, and we have Poincaré inequality, which, how to say, follows that velocity in some framework vanishes exponentially. So then all integrability is important, because you must know that as we have this portion, so somehow we need to code regularity of the surface. So it's changing, and within the time, the constant in linear system may grow. So the only way to control it is just to control, say, the property of the construction of linear estimate, and this is related to more or less with roughness of this object. And of course, the weaker information is integrability. So how to understand better? So here is definition of my favorite Lagrangian coordinates. So this is streamlines, as someone wished to call it. So in general, we have the following picture. So we have the particle here, and it goes somehow like this. So here is t equal 0, and here is t equal t1. And then, as we see at time t equals 0, x and y is the same. So here is x, which is y. So in order to define y, which is our Lagrangian coordinates, we need to go back on this characteristic here, and then we obtain the change of the coordinates. So this is called sometimes particle coordinates, or usually we call it Lagrangian. So this is related by the position of initial particle. And what is important is properties of the velocity. So we see that the velocity must, in order to solve it, must be Lipschitz in terms of this x, but also we need L1 integrability just in order to define this x globally. So as we have this interface, to have possibility to control the change of this interface, we need to have L1 integrability in time. Okay. So there is no any magic just to remove all nodes. Okay, doesn't matter. Okay, so our approach, and here is how to say break for anecdote. So at this slide, we see dark side of knowledge, because all people who are working in abstract maximal regularity theory say that this Z, as we think about it, is impossible to get. So some years ago, I have no idea, probably 10 years ago, we were sitting in bar in Bendlevo with Rafael and Matthias. And we are talking about mathematics, because sometimes after some days of talking about everything, people in bars start to talk about mathematics. Sometimes it's happened. And he was claiming that our result with Rafael is completely nonsense, because it's impossible to get maximal regularity estimate in this space. And this is related to the well-known, for people working in this theory, fact that X must be UMD space, and due to basic properties, must be reflexive somehow. This space must be reflexive, and this is the general tool in order to obtain LP-LQ estimates, so maximal regularity in that we have in LQ as a X, can be some Sobolev spaces, and LP in space. And then all this P and Q must be, we call it finite, so greater strictly than 1 and less than infinity. So this is the portion of the theory which all people at the very beginning of meeting of abstract theory says. But then we took a piece of, we took napkins, and we took this example. We took this example, UT minus, heat equation over the space. And using very short computations, having in mind definition of Biesov space, we are able to show this type of maximal regularity estimate. Without any problems, it is enough to look to our papers with Rafael, for example, about heat equation. There is an example how to fastly show this estimate provided that X is Biesov space. And of course, there is no disagreement with the general theory because this space is not reflexive at all. So we have some general thing which is more or less complete. Theory is horribly complex, but good point is that we are working in classical spaces. As we want to have L1, so then this X must be not reflexive, and this is example of unreflexive space. Okay, so this is Biesov space, and of course,
what are you trying to do, Piotr?
Okay, and of course, knowing that some of you are lucky guys and has no idea what is Biesov space, so usually we divide people in two groups, to happy one and that who knows definition of Biesov space. So the easiest definition is through real interpolation. As we have real interpolation, so then as we consider Biesov space of SPS, of course in some regime of S and Q, so then as we make interpolation of LP and W1P, so then we obtain Biesov space. It has its homogeneous version, where these dots, this is very important, says that W1 dot is just gradient of U. So here is the highest derivatives. And what is important here? Why this information here is distinguished between these two the spaces are important? Because in case of the whole space, in order to obtain maximal regularity estimate here, we need to use homogeneous spaces. So inhomogeneity says too less information about the behavior of, we call it lower fluctuances. So as we look for Fourier transform, so it does not control situation what happens near origin of the Fourier transform of the function. So from that reason, this is very important to control these homogeneous spaces, but of course, then everything is rescaling and all these computations are very, very simple. I'd like to avoid definition of Biesov spaces in, how to say, kosher way by parallel decomposition, because then I will spend more time and, how to say, result of my talk will be that you will concentrate on the definition of the notation of this function, but this is not the case. I wanted to show something more general related to this abstract theory. And as someone really dislikes to have this very abstract approach, there exists some, say, Biesov, originally Biesov definition by different quotient. So Biesov spaces with index Q equal 1 can be defined in that way. So all, of course, these definitions are equivalent, and there is the whole theory concerning this story, and people from functional analysis very often are surprised that someone is using their results. Okay, so now we think about abstract theory. First of all, application of Biesov theory in free boundary spaces in bounded domain is very, very complex. The problem is that definition works very nice as there is no boundary, and there is the boundary, so then we need to use some different approaches. Of course, we have definition which says that all these things are equivalent by suitable extension and so on, but this approach does not fit very well to real application. So as someone has a time, so it's enough to look for our monograph of with Rafael, where we consider external problem for stock system. There is many of tedious computations, and idea was if there is a help of abstract theory in order to create simpler way to obtain the result in Biesov spaces. And with help here appeared Matthias Hieber, and he said us, okay, I found a result, classical one. So this is also funny because this result from 45 years ago. Yeah, I wrote this here, 45 years ago, so almost the half a century. They proved this result about, how to say, very abstract approach based on real interpolation. So I have no idea what is the reason that result maybe not was forgotten because people know it, but never applied to the Biesov techniques. But probably the reason is that, say, 20 years ago, no one knows what was the Biesov spaces, and they were very afraid of this language. Now this is, I mean, not so scary. Okay, so what D'Abrato-Griswold theorem is? So just for, this is just a sketch. I do not go into details. I have no time, and in general, this is quite difficult. So we have analytical semigroup, and then we consider, say, abstract ODE, for which we have Duhamel formula as a solution. So A is linear, is time-independent operator. So what is the first problem of application of semigroups is that requirements about the A is that we are not allowed to put here explicitly T. So this is the first problem. So somehow, as we think about stability, so then we need really to have something which is fixed in time. So then we have this object, and very important thing is domains of operators. And we need, again, distinguished domain of operator and domain on homogeneous operator. We call it dot. So the difference is that as we have ground space, so as we think about LP, LP system, so we think about A, which is just Laplacian, or of course minus Laplacian. And then ground space X is just LP. So domain of operator A is just W2P. But as we think about homogeneous part, so then this is homogeneous space. So of course, there are some problems with definition of it, because we know that as we consider Sobolev homogeneous space, so the same is for Biesov, as this index 2 is too high, so then this is not a Banach space. So we must be very careful in some definitions of the density and so on, because this is not all the time clear what is it. But fortunately, we have Patrick, who did his PhD in this abstract analysis, and he is correcting our mistakes. Because very often we just think that everything is the same, but then it appears that this is not true. Okay. So in order to define the Griswold-D'Abrato theorem, we need to define such a, say, space. I won't define it because what is important, this space is, under some conditions, of course, equivalent to interpolation space between X and domain of operator. And the D'Abrato-Griswold theorem says that as we have theta, which is between 0 and 1, Q can be 1, this is important, and T can be infinite or finite. So then for all F in this space, the solution to this abstract Cauchy problem with, say, x equals 0, this is just technicalities, satisfies like this, that U belongs to the domain of almost all T, and then we have homogeneous bound. So operator U belongs here, provided we have estimate in this space. Here, both are dots, so this is homogeneous spaces. What is important is that Q can be equal 1. So this is very crucial thing. Q can be equal 1, and thanks to this, we can apply this theory to our problems. Okay. Now, as we have this tool, this is very nice tool, we go to, how many time I have?
You have -2 minutes, Piotr.
This is amazing because I was afraid that I will talk just 10 minutes.
Okay, well, so maybe very quickly you can say something about this application. We will ask probably about it anyway, we would. So...
Okay, but anyway, I have the picture, as you see.
Yes,
again, about
nice.
free boundary problems. I spent plenty of time to fix it to LaTeX version, so give me opportunity to use this picture at least. So, okay, so now we'd like to make an application of free boundary problem. So we see again, this picture is very nice from the viewpoint of, say, people working in this field, because here we have this regular part. Here we have edges. Edges are not so bad in general. It's probably under control, can be under control. And here we have this part, white one, which is completely out of classical control. So here is a completely mixture of water and air. So using these techniques, we are not allowed to do this. So we applied it for Navier-Stokes equation with free boundary problems. And as Michał said that this is over, so I will just put it the last slide. Thank you.
Okay, thank you very much, Piotr. Yes, are there any questions or comments?
No.
Of course there are.
Of course there are.
I wonder if Yoshi wishes to comment on his work, on this work.
I could guess Professor Zacher could have questions or comments to that as well.
Yes. Yes.
So please go ahead then.
So you have this space L1, and then in this with values in the base of space. So I mean, for the nonlinear theory, it's of course important to have also knowledge of the natural spaces for boundary data and also for the initial values. So do you have precise characterization of the natural spaces for the data? And you need it like a phase space, a trace space, right, for your problem. So this you should know.
This is indeed a very natural question, and the theory answer it even on the very general case. So this is some kind of interpolation space between domain and the ground space. And in our case, this is L1. Where it is? L1 space. So maybe I will go to the last slide. This is the best because I didn't say it. So in general, we have this theory, but using, I didn't tell the most important thing, but maybe this is the point. So as we consider linear situation for the Stokes system, so then we obtain the following estimate. And thanks to the situation that this Q is equal 1, so then we lost 2 derivatives. So this is amazing because the trace space is the same as a ground space. So this is very, how to say, it is really simplification, because in general, as we have, say, LP spaces, so here as we have LP, so then here we have some Sobolev space. So let me write it. So in case as this x, no, I have some more y's. X is LP, so then trace space in this situation is okay with dot is like this thing. P. This is Slobodetsky space, so this is equal BS of PP. So this is classical objects, and here we have the specification by in case as we consider LP in X, of course. So then we have the specification that this trace space is a real interpolation between these LP spaces and others. So this theory is done. I hope soon we will get it as a preprint. But I told there is plenty of technicalities and plenty of how to say elementary results which must be restated for format, restated for all this how to say special language of divergence-free system and others. What's important, because I didn't say it, so maybe I will answer, is that in order to apply this Dabratov-Griswold theory, there is no need to repeat all these computations in Biesov space. It is enough to have LP estimate for resolvent. So this is, I mean, in order to get it, it is much more easier than in evolutionary case. So this was the reason. This was the reason I remember as I was talking with Yoshihiro Shibata about our result with Raphael. So he was very upset on us, on me particularly, that we do not create any theory, but we are just create some toolbox, and after some tedious techniques, we are obtain the result. So here is the theory. So provided we have the resolvent in LP spaces, so this is much more less technical job to do, then we get this type of estimate. Say almost for free.
One more question. So I see you have L infinity with values in this trace space. Do you also have continuity?
This is continuity. I mean, there is no problem to say with continuity, but the problem is just our, how to say, superstitions that continuity is a prohibit space in maximal regularity. So of course, here is continuous function in values is this. This follows immediately from the fact that here, maybe write it, let me write it, that here as we look for the equation, it's not only this. We have also here this VT in this space.
Of course.
So in order to get this V, we just integrate in time. And this integration gives us immediately the continuity. So what is important, this is continuity at t equals 0. So as we consider nonlinear problems, so then some of these results are not clear, but here there is no problem.
So in this LP business, there are now also some results where you apply weights, time weights, right? So in using time weights, you can reduce the initial regularity, right? So
yes and no.
Maybe did you look at this in this L1 setting? Is it possible, or is there no?
Put it in that way. There is.
You know what I mean? There are these time-weighted LP estimates, right?
Yes, of course. You are right. I mean, as we consider just classical semi-group approach, so there is only, say, continuous dependence on time, or L infinity dependence on time with estimates of weights in time. So now what we doing quite often is that we cut off the initial data by this time weight in order to save regularity and then get better regular estimate, but with time weight. This everything works quite well But then there is a problem of right-hand side. Maybe put it here. That as we consider time weight, so then as f is really given, and this is the case of free boundary problems, because this is somehow, here is a coded initial boundary after the linearization. So then, as we test by time, so we do not improve regularity of this. As we have non-linearity, so then by bootstrapped, of course, we get it. Mm-hmm. So here is quite technical situation, but this waits time. Now we are preparing with Patrick and Rafael quite interesting paper concerning Lorenz spaces, where this time weight is crucial. But again, this is the situation that we have, say, full space, we have simple nonlinearity, and then thanks to this time space, Lorenz space, and other strange things from functional analysis, we are obtain quite fast, very strong result. But you are right that nowadays this time weight is very important, in particular as we want to show uniqueness. So very many techniques based on it. And what is surprised, these time weights are, say, irrepressible as we consider compressible fluids. So when vacuum appears, so then we lose all information about regularity. And then as we apply this weight time, so then we are able to get some, say, important or lost information.
You mean it is crucial in the compressible case?
Yes, this is crucial in compressible case, and somehow this is easy to explain because as we consider continuity equation, so all estimates are L infinity in time. So indeed, we can apply there this magic of the semigroup and multiply this by t to power minus 1/2, and all these things will survive. So this is related to some technicalities, which of course on the level of linearization is quite natural, because in order to fix, for example, L2 estimates in a space which are scaling invariant, so then we need to use time weights.
Okay, thank you.
You're welcome.
Okay, thank you. By the way, so could you show the previous slide to that one?
This one?
I was just, the one that you showed. I was just wondering, because there was supposed to be some free boundary, and here you have just shown this Stokes system. So
this is not my fault. This is fault of the chairman. He stopped my lecture.
Yeah. Sorry for that, but you know.
No. I obey all the time, chairman. So okay, thank you for this question, because on this slide we have the answer on it. So as we consider free boundary problem, so then we make Lagrangian coordinates change, and then there is no problem, because from as we have initial time, so t equals 0, and here is t equals 7, yeah. So then this Lagrangian coordinates makes our system defined at the initial time. So the domain is the same as the initial. So this is fixed in time. So thanks to this, we just make a linearization. The price is a nightmare. So really, we have plenty of very strange objects. And in the general, as we are using Lagrangian coordinates, so then we have the mass with change of the operators. But here also there is a part concerning free boundary problem. But still, this is the simplest approach, because all these, say, new terms are somehow garbage from the viewpoint of regularity. So we have the number of it, but this is controlled. More difficult things are here, as we have these parts related with not zero condition. It appears that this is more difficult to remove, and in order to remove it, we need to do this, say, by hands. So we need to find a good extension. So here is coded famous Bogowski operator, and here is just hard job.
Okay. Okay, thank you. I got my answer. We might have room for maybe some other quick comment or question.
Ask just at the beginning, Piotr, you talked about stability. Did you obtain a stability result?
Yes, somehow this is stability result because where is this theorem? This is the theorem. So as we got this situation, so say good point of this theory we created is that we are able to solve something which is unsolvable now. So the free boundary problems with non-compact boundaries. So the good example is half space. And then the result shows that this half space is stable. So as initial domain is very close to half space, and then perturbation of the velocity is very small in proper space. So then all these objects remains close to initial data. So since this is small, so of course these norms also are small. The definition of this norm, I mean, the bounds of this norm is done through fixed point Banach theorem. So then C generates C plus C square. So this is still small. And this is important that we get it. What is funny in this stability? We show that the domain is close to R2, I mean half space, but up to a shift. Because what we control, this is this guy. We know that this is small, but we do not control this guy.
So do you have convergence?
I mean, this is not a convergence, this is the question of definition. So since we do not control lower norms, so then this plane can move. This is the problem is with definition of, say, this is the unbounded domain. So many integrals are not defined. So we solve it on the level of the Lagrangian transform where everything is fixed, and then we reverse it. And then we look what we control, what is not controlled. So thanks to the fact that we control this object, so then we are sure that we have diffeomorphisms between Eulerian and Lagrangian systems. So this is somehow important. But then it appears that using this optimal framework, we are not control this and this at once. And this is more or less a shift. We, of course, locally in time, we control it. But for globally, it may happen that we have shift to infinity.
So it drifts, the waves drift away.
Something like this.
Yeah, cool. All right, thank you.
You're welcome.
Let me ask you a question, a quick question, hopefully. Can you solve with this technique the problem of an ice cube melting in a glass of water? So we have actually two free boundaries.
Using these techniques, provided this cube of ice, definitely locally in time, provided the shape of the cube is not so rough.
This is an ice cube, so this is a Lipschitz.
Lipschitz is not nice.
Okay.
I mean, this regularity here says, this is very rough regularity, but this regularity says that normal vector is continuous.
So, okay, suppose you have a nice ball.
A nice ball. So locally in time, we can do this.
Okay, fine. Perfect.
So in general, as we would have a shrinking system for some ball or something like this, so probably there is a, say, subjects for PhD that we are able to get almost the end of the ball as this is melting, as we have the, say, some symmetric, some well behavior, because of course, as I told, for general shape, there is a problem with this geometrical catastrophe. But in the case of such a, say, ball, which is shrinking to the point, I believe it's possible to show for small perturbation and so on.
Okay, I'm sorry, but the time for questions is up. So let's thank Piotr again. We can.
Thank you, thank you.
And I remind you that if someone is interested in discussion with Piotr, for instance, or with someone else in a smaller group, then he may say so to Piotr Rybka, the organizer, and there are these breakout rooms. I don't know how they work, but I know there is such a possibility.
No one was willing to do this, yes? So
not yet, I don't, but there is this kind of possibility.
Yes.
Okay, yes. So thank you.
And right now we will have a talk of Lorenzo Giacomelli. Lorenzo, are you here?
Yes, I am. Hi.
Okay.
Ready to start.
Hello. So please prepare. I suppose you have some slides.
I'm fine. Yes, I should share my screen. And here is it. Is that okay? Everybody's hearing? And
I hear you and I see the slides. So
very well.
Okay, very well. So we have now Lorenzo Giacomelli from Sapienza University of Rome, who will speak about the one harmonic flow. Please go ahead, Lorenzo.
Thank you very much. This is going to be kind more of a review. Thank you very much, first of all, for the invitation. I'm happy to be with you, to see you all again. As Salva told, that's a good initiative, and I appreciate it. Okay, this is more of a review, as I told you. I mean, there are no brand new results. Say 1 year ago, that's the most recent ones. And but I like to advertise this problem in the hope that someone gets inside this. I think it's a nice problem yet. These are only first steps in these directions, which I took with people you see there: Roberto Dal Passo, Agnese Di Castro, Michał, Jose, and Mazon and Salvador, who are here, I guess. And okay, I was asked to make a 20-minute talk. Probably I'll be quick, but never mind. And so there are kind of I erased a bit of a framework and also related topics such as the two harmonic flows, the total variation flow. And so there will be not much references to these related works, and I apologize for that. Okay, so what's the setting? The setting is we are given a domain omega in Rm, and we look for a map U, which will be in BV spaces to a Riemannian manifold N, which you can think of as being all nice properties you may think of, connected and embedded in some Rn. And so just remember, little m is the dimension of a domain, and little n is the dimension of a codomain of a Riemannian manifold. Okay, and so the basic object is the total variation of this vector field. So the total variation of this vector field consists, can be represented, say, as a diffuse gradient, if it's a BV function, if U is a BV vector field, as a diffuse gradient plus a component on the jump. And it's known under reasonable assumptions on the manifold that this at the jump point, what counts is the geodetic distance between u plus and u minus. So as you know, BV functions have a jump set where they take two distinct limits, and say these two distinct limits are u plus and u minus, and the total variation at that point, total variation measure the jump, so between u plus and u minus, taking the length of a geodesic, which connects u minus and u plus. This is to just to fix the setting. Okay, so remember u is a vector field, but it's constrained to take values in the manifold. Okay, so and the real interest of this in this to me is the gradient flow of this functional, say with respect to the L2 metric. Okay, that's formally written as of course ut equal minus the subdifferential of E, very formally written like that. So I take an initial value and I let U evolve in order to decrease the total variation, go in a gradient flow of a total variation function. Now, there are two things to be said right at the beginning. There are two cases essentially. One is the case of non-positive sectional curvatures, in which, for instance, in the flat space Rn. In this case, the energy is convex, is a nice energy, and therefore you can appeal to abstract gradient flow theory and extract existence and uniqueness for the abstract gradient flow. And that dates back to Uwe Meyer in '96, which kind of anticipate what later on will be framed in the Ambrosio-Gigli-Savare theory of gradient flows. But this was done earlier by essentially the same kind of tools. On the other hand, there are, take the case of a sphere. Suppose it's just the sphere in R3. Then it's an observation. You can construct by hand a counterexample that the energy is not lambda geodesically convex, whatever the lambda. So it's not convex, it's not geodetically convex, and it's not lambda geodesically convex for lambda. So it doesn't have any convexity. This means that you cannot really apply gradient flow theory. And that, in some sense, motivates looking at the PDE for the gradient flow. Okay, so you have to take a different approach, and naturally, that's the one we take. Okay, so if one writes the PDE, you make a formal computation. It's again quite formal. You see immediately from writing that it's a formal writing. You get ut equal the projection over onto the tangent space at point u of the divergence of z. And z, that's a notation I shall use frequently, is the gradient of u divided by the modulus of the gradient, modulus of d. Okay, so if there was, if the space was flat, if the target space was Rn, there would be no projection, and you would get exactly the vectorial one Laplacian. Okay, so the vectorial form of the total variation flow. But since there is a constraint, you have ut has to be tangent, and therefore you get this projection. You can write it in couple of minutes in the formal way. Okay, so as for any PDE, there are two ways which can be used to approach, at least, I mean, two ways in which we can approach and study this object. And so the first one is to look for smooth solutions in a sense that I will describe later, right now, actually. And the second one is to look for solution in the natural energy space, that is BV function. And I'll try to say a few things on both. Let's start with smooth solutions. So we look at the PDE, we take, say, homogeneous Neumann boundary conditions or periodic boundary conditions. That's the least problem. Okay, so what about smooth solutions? And let's remove the brackets around smooth. So let me first state what it's known. Yeah, it's what happens is that if the initial datum is Lipschitz continuous, then you have a unique local solution which is itself Lipschitz continuous for all times. And if in addition the space is has non-positive curvatures, or if the domain little m is one-dimensional, then the solution is global. This is a result we obtained together with Micha and Salvador in was published 1 year ago, and there are earlier results by Giga and collaborators in 2004. So there are two comments to be made here concerning smooth solutions. The first comment is, of course, why Lipschitz? Well, Lipschitz is the best you can do in this kind of problems. Because, for instance, if both the domain and the target are one-dimensional, then the total variation flow, which is the 1D analog of the object we are looking at, has at best Lipschitz solution. You start from a C infinity initial datum, and you will immediately develop a Lipschitz solution. So there is no way to improve this regularity. So smooth means Lipschitz in this framework, and not more than that. That explains the framework. And of course, then one may ask whether local solutions is a technical obstruction or a substantial obstruction. And the answer is that it is indeed substantial. I mean, it's a fact of life that singularities may appear in this kind of problems. And it's well known even for the two harmonic flow. You don't need to go into the specific framework of one harmonic flows. You can stay in the more traditional framework of two harmonic flows, but there it is also known that singularities may develop. These are codimension two singularities, which are called vortices, and which may happen in finite time, even if the initial datum is completely smooth. That's an example here in the picture is if you take U from the unit disk to the unit sphere, which in the bottom left picture is kind of I tried to depict. So the arrows are the values of U. So these are unit vector fields. You take an initial datum like this, so which is parameterized by the angle h, and then you rotate it. You rotate you rotate it in order to define it on the whole of D2. Okay, you let this thing evolve, and as you see in the right-hand picture, in the right bottom picture, if you start above a certain threshold, capital H, or at a certain threshold, capital H, for the, so if the angles vary enough, then at finite time you will develop a singularity in the angle. The angle at 0 will jump at pi. Okay, so local solutions cannot be improved in general if the target manifold is at least has some positive curvatures, like the sphere. Okay, maybe I have one minute more to explain you why, how do we get the Lipschitz bound. This is something simple and interesting to me, so I would like to give you a few words on how we get the Lipschitz bound, because it's interesting and maybe enlightening for what will follow. So now this is a completely formal argument, of course. If you want to make this idea rigorous, you have to introduce clever approximations under which these estimates are stable. Yeah? But I avoid introducing them for the sake of simplicity. So let's just think that everything is smooth and non-zero and has a perfect sense. So this the basics is an a priori estimate, as often, and it's an a priori estimate on the time derivative of the integral of du to some power, some high power q, divided by q. Well, that happens to be a nice object in the sense that there are many things which have a good sign, which I didn't write. So some integrals which have good sign, which I didn't write. And there's a right-hand side which survives with possibly a wrong sign or without any sign, which is which involves, as you see, the Riemannian tensor. Now, now what happens? Well, that it happens if little m, if a dimension of domain is 1, then the estimate is just trivializes, and if the estimate trivializes, then you just have to pass to the limit as q goes to infinity, and you get the L infinity bound by the fact that all these q norms are decreasing in time. And that means that you have a global bound and therefore a global solution when you use this estimate in the process of approximation. The same happens when the manifold has negative principal curvatures, and that's exactly the same. You get the minus sign. Right. But this a priori estimate is useful also if you are in a generic manifold. Because in that case, you see from counting numbers of derivatives and counting numbers of u's that what you have is that the right-hand side, I mean the measure inside the integral on the right-hand side is bounded by du to the power q plus 1. Yeah? And that tells you that you can say bound the left-hand side by the right-hand side. It's a kind of ODE argument now, which after, so you get 1q more, so you take 1q more, one exponent more out with the L infinity norm, and eventually, when letting q go into infinity, you will obtain that dt of the L infinity norm of a gradient is bounded by the L infinity norm of a gradient square, right? And now it's an ODE argument to conclude that you have a local solution and you have you of course also have a uniform control on the time interval before blow up. That's for the Lipschitz bound. That's something we obtained together with Michał and Salvador. And one interesting point to be made here is that if little m is 1, so again, if the domain is one-dimensional, the estimate can be completely localized in the sense that you can say that you see the formula, the Lipschitz, the value of a derivative at the point x is bounded by the value of a derivative at the initial at time 0 at the same point. Yeah, so it's an estimate which really goes along the vertical timeline of any point, which reminds of the picture we saw before, right? That maybe I go back a little bit. You see the picture here is exactly the same structure. Yeah, so vectorial and scalar in one-dimensional domain have this analogy, but this was not known before. And this is an observation of Michał essentially, and that was the starting point of something which I will try to describe in the last slide. Okay, that's all I wanted to say about the first class of solutions, which are smooth solutions, and then smooth in the sense of Lipschitz. And now let me go quickly to BV solutions, in the sense solutions in the energy space. Here it is convenient to introduce a second and equivalent form of the PDE in which somehow I develop the projection. The projection is developed, and you can write the equivalent form on the top right part of the screen. UT equal the divergence of Z plus the second fundamental form, which I will call mu. Yeah, just for notation. The story started with works by Giga on piecewise constant initial data and also with smooth data, which we already saw. What we did is what we did with Mazon and Salvador was to get a result for generic initial data, like instead of piecewise constant, but only on the octant of a sphere, yeah, where the geometry is much simpler because of all the symmetries of a sphere. What we obtained, let me just remove this, sorry, yeah. What we obtained is that there is a characterization of this measure mu, which appears on the right-hand side. And this measure mu happens to be what it should be on the diffuse part, in the sense that for the sphere, for a smooth function on the sphere, that guy is exactly the normal to the sphere times the modulus of a gradient. Okay, and you see on the picture what UG is the geodetic midpoint between the two. But that's that was well, I mean, we were very happy about this result because it was certainly something which we have been trying to do for a long time, but the interpretation was a bit unsatisfactory because, I mean, neither the normal nor the geodesic midpoint are a really sound object from the point of view of interpreting these results. Okay, this is a correct notion in the sense that in the case of S1, we also got uniqueness. So then I started to wonder we all started to wonder what would have been the right notion of solution for a genetic manifold. I made a remark together with Agnese. She was a postdoc for 1 year, and in S1, this is a practically trivial observation that due to the symmetries of the sphere, this mu, which you see above in star, is actually the same as taking the geodetic between 2 points, u minus and u plus, taking the tangent vectors to the geodetic, and taking the difference between the two. For the sphere, or for the circle, for the sphere, these are exactly the same thing. And you can easily make a computation. But there are reasons to believe that this is the correct notion in general. Why is it so? Well, because if you think that you are going from, in a jump point, you are going from u minus to u plus along a geodetic path, say, let me call this point gamma, then along a geodesic, mu is equal to minus the second derivative of gamma times the modulus of a gradient of u. And if you approximate this by different quotients, then you exactly get the difference between the tangent vectors which are there. So that was a more natural candidate with respect to star for giving a meaning to the measure mu. And you see a much nicer relation between, okay, that I'll display this. Okay, so let me go to the last slide. This is the past, say in some sense it's past, and the present is what we are currently trying desperately to finish since quite some time with Michał and Salvador, which is exactly the 1D case, in the case in which the domain is one-dimensional, but the target is generic. And there we think that we have a characterization of a measure mu in the sense of what I described before, and a characterization of the vector field Z at jumps. The diffuse part is not a problem. And moreover, we know that with this notion of solution, the solution will be unique and will coincide with the gradient flow solution if the manifold has negative sectional curvatures. So this is a notion which will be consistent, which is consistent with the gradient flow solutions in the case of spaces with negative curvature. And the idea, of course, why little m equal 1, so why the domain is one-dimensional? Well, it's because we heavily make use of the fact that we have this completely local estimate, which I described before, in which the gradient is estimated timeline by timeline at each point x. Okay, that's essentially all I wanted to tell you. There are, of course, after that, one would like to handle case m larger than 1, where there's something we can do in the case of non-positive sectional curvatures, but it's still embryonic. And there are very interesting open questions. To me, first of all, of course, is uniqueness, which is known only, as I told you, if a space is negatively curved, or in the case of a circle. And there are regularity and qualitative properties, analogous or non-analogous to the scalar case, to the total variation flow, which need be explored and which would even help you in uniqueness, because uniqueness and regularity or qualitative properties are, as you all know, are deeply related. If you have one, you may have the other, and vice versa. For instance, would be interesting to know if and how the jump set evolves in time, whether there is a decrease of jumps in this frame. Right? I'm talking about now the case of Euclidean homogeneous norms. Yeah, that's more or less what I wanted to tell you about the general picture on this problem, hoping that some of you may get interested in that. And now let me conclude. Since Piotr Mucha has revealed the secret, I can thank you for your attention and wish happy birthday to Piotr.
Thank you. Thank you, Lorenzo.
Thank you, Lorenzo, for your talk.
Thank you.
I hope there are some questions or comments, but first of all, maybe I would like to make a comment on what you said before about these smooth solutions.
Yep.
Can you go back to the smooth solutions?
Sure.
So I think you, okay, not so far, or I don't know. I think it was when you were speaking about existence in general for the smooth solutions.
I think it's here. Look at the above.
Okay, you have this. Yeah, I just wanted to point out that you didn't mention that we need to assume that the domain is convex. This is kind of a technical thing that we have in that paper, and it's essential for this a priori estimate that you have written later on. So that the boundary term, especially because we cannot localize, because the one Laplacian is so degenerate that it does not allow for localizing of this estimate. We need to do this kind of estimate up to the boundary. That's why you have the integral over whole omega here. Yeah, so that's why we need to have convex domain. And well, we expect that it's just, I mean, or at least I expect that it's just technical. But these kind of estimates are kind of open even for scalar total variation flow, so without any manifold in the image. So recently there was, I mean, if you don't have convex domain, if you have convex domain, then they are maybe known or expected. Actually, you have a preprint with Rybka about this kind of thing, with Professor Rybka, sorry. Yeah, when the domain is not convex, then there is recently a preprint by Alessio Porretta, actually a paper now, where the preservation of L infinity norm is done, non-increasing of L infinity norm, but that's just for scalar total variation flow, and it's also not obvious how to move to this case, but maybe we can also do this in this case. So yeah, okay, I just wanted to point out this issue with convexity of domain. Okay, and now any other questions or comments?
Yes, if I may.
Sure.
Lorenzo, could you go to the last slide showing mu? I have a question. I have an impression that this definition of mu requires that your manifold should be generic. I mean, it should be embedded into Rn.
Sure. No, generic, I mean not S1 or S2 only.
Yeah, but I mean, it should be embedded, because otherwise, if you have an abstract manifold, it's rather difficult to compare anything different tangent. It's difficult to compare tangents at different points.
Correct. And we also assume that it's completely connected, and we also assume that the jumps are not too far, at least for positive curvature, so that there exists a unique geodesic which controls that. So there is a there is this is for the result is for initial data whose jump are not too large, so that there exists a unique geodesic, well defined, and exactly as you said, it's at least embedded.
And if I may continue,
Sure. But I would also like to comment on that issue, if I may. That sure. I was mostly asking Piotr, but okay, thank you, Lorenzo, as well. I just wanted to say that about this, in general, this equation is kind of embedded because you have this A. A is the second fundamental form of our manifold, and this is already an object which you have when you have embedded your manifold. Yeah, we always consider it embedded. It's for a complete manifold. This is basically without loss of generality that we can have it embedded. But actually, to me, this kind of this form of the equation, maybe it's not essential somehow, but the interesting thing here is the identification of Z really on jump points. This is kind of equivalent, because then if you have identified Z, see here you have this equation Z plus minus equal to T of U plus minus, okay? So this is now just completely geometrical. Okay, to write that, you don't need to have an embedding because the tangent vector is defined in Riemannian way. Then, if you want to write somehow this main equation in some coordinates, you will get this mu, which is like Lorenzo wrote. So, yeah, I wanted to add this kind of thing. Okay.
I agree completely.
If I may ask another question. I got an impression, please correct me, that you don't like the counterpart in the data.
No, that's something it can be handled. The counterpart, I don't say that I don't like, I say that it's the diffuse part is less problematic from the viewpoint of proving things and characterizing objects. If you see here, I concentrate only on the jump set. I practically forget in my presentation what happens on the diffuse part. That's to save time, but it's because it's the most interesting and difficult part, the identification of the jump set of Z and U.
Thank you.
Thank you for the question. Now there is a question by Yoshikazu Giga here in the chat. If we measure jump, okay, maybe you want to ask it yourself, Professor Giga.
Yeah, it's a very nice talk, and I have elementary, maybe simple question. In your case, you measure the jump by intrinsic distance, but if you measure the distance by extrinsic, using extrinsic distance, if you measure distance, if you measure jumps by extrinsic distance, is it possible to prove the existence of a BV solution in your setting, or you use this the geodesic? You use the distance measured by geodesic distance is substantially or essentially used? Not. This is my question.
Yes. Okay. Yeah. The answer to me, when Micha and Salvador can, of course, correct me, but to me, it's the natural object is the geodesic distance, because right away from the first slide, that's the proper relaxation of the functional when the target space is immense. Then from a technical viewpoint, I guess that we use it very much, in the sense that we use it almost always, starting from, the fact that the function is lower semi-continuous, and the lower semi-continuous limit is what you see on the right-hand side, which has geodesic distance. Well, that of course it's not essential, because you would get something smaller. But
so thank you. Yeah.
Yeah.
If I may, I would also like to comment
Sure.
that I mean that's kind of essential thing for us. I mean that's what we work with. We basically consider smoother approximations for these problems such that they are inside of the manifold. We want to have something intrinsic. So that is like basic part of our work. So we didn't consider basically this question if we want to have this extrinsic distance. It's actually interesting. I mean, to me this is interesting because if you just consider extrinsic distance, you could maybe consider any set. It doesn't have to be a manifold then, right? But you can just consider any constraint, and well, it
have a singularity.
Would be interesting what happens then. But this is not something that we considered at all.
Thank you.
Also, from the point of view, maybe we did it maybe with some applications in mind, that in these applications you really want to be somehow constrained in your manifold and you want to consider this distance which is somehow intrinsic in the manifold. But for sure, I believe there might be other applications where you have where you just consider any set and you consider extrinsic distance.
One merit of extrinsic distance, it's easy to calculate, right?
Sure. Yes.
So I want to ask something about this question. We were trying, together with Mazón, Fuensalvador, with San Casellas, for a long time to obtain results using extrinsic distance, and we were not smart enough to get any result for the sphere. And that's when we exactly discovered that the relaxation was not with extrinsic distance. It was when we were able to produce something, produce a result. So it's not so easy, I would say.
I see. I didn't know actually that you tried at first with extrinsic distance.
Yeah, during many years.
It's a long story.
Yeah. I mean, the result of Quintamucci is 2006. So I think that this goes, Mazón was first studying this in the 2000. So we were not aware of this result.
I see. Okay, any other questions or comments? I don't see anything. Maybe somebody could still have something, but in any case, I wanted, since we still have most of the participants, and already twice there appeared somehow well, the question of Professor Rybka's anniversary, and Professor Rybka instructed us yesterday to prepare some drinks. I don't know if anybody has drinks prepared at the moment, or are they already? You have some, or maybe you already run out. Maybe you still have some seconds to get some drinks. Okay. This is not the same bottle. I thought you just emptied this amount from that bottle you showed before.
No. Still, this is not open.
Okay.
Cheers.
Good. Let's wait for Salva. I think wanted to get the drink too, and he didn't come back yet. So. Okay, we have Salva now. Salva, are you prepared?
Cannot open it.
Okay. So just yeah, Piotr, I think maybe it's best if you wait, and yeah, it gets some air or something. Okay, so now Salva is prepared, so let's hope that Piotr, Professor Rybka, lives to at least twice this age, and let's drink to that.
Cheers. Thank you.
Cheers. Zdrowie, Piotrze, zdrowie.
Cheers.
Dzięki. Przyda się.
Salute.
Salut.
Na zdrowie. Salut. Kampai.
Okay, so again, best wishes to Piotr.
Thank you.
And thanks to all the speakers of the morning session.
And the participants.
And the participants.
Thank you. So I guess we shall meet in 5 hours.
Yep. Okay. So see you then.
Yes, exactly. We meet in 5 hours for the evening session. There will be Sabrina Roskani, right? And Adam Kubica. So see you in the evening.
Goodbye.
Bye-bye.